This report is devoted to a new approach of exploration of plasma expansion process of pulsed plasma source. The plasma source examined was the height current vacuum arc discharge. Introduction. Typically, high current sources are created as pulsed with a plasma generation duration of several microseconds. This fact leads to the point that all processes occurring in such plasma sources are significantly unstable. In particular, thermal processes at the cathode and anode differ significantly from the case of stationary source. But the main feature of the unsteady nature of the plasma flow. In pulsed sources of the microsecond duration range, a large volume of plasma propagates into the vacuum. In this process, the collective nonlinear effects become significant, which are characteristic of plasma at high gradient of densities and temperatures. To analyze such a phenomena, a method was developed using a set of small-sized ion analyzers located in different positions to the plasma source. Next slide. The slide in this slide depicted the scheme of our plasma source. The discharge gap was built according to the Coxell scheme. A is anode. A voltage pulse was applied to the cathode. The anode. The discharge was ignited by a breakdown between the cathode and anode through the surface of dielectric ring. The cathode diameter was 1.5 millimeters. The dielectric ring was 6 millimeters. High pressure polyethylene was used as an insulator. This is a picture, the photo of this electrode setup. The current waveform. The shape of the discharge current is shown in the figure above. The total duration of the pulse current was about 15 microseconds. The maximum current was reached to 6 microseconds after the start of the discharge. One can keep in mind that the current waveform does not contain any sharp bursts or sharp falls and increasing of current. The very smooth waveform. Experimental setup. This picture shows the plasma source and the set of small-sized ion detectors. A set of 4 identical small-sized ion detectors was used to analyze the plasma flow. The detector diameter was about 6 millimeters. The entrance aperture consisted of a set of holes 200 micrometers each in diameter. The ion current density was measured using a Faraday cup, 4 millimeters in diameter and 5 millimeters in length. The detectors were located at distances of 140 millimeters, first detector, 155 millimeters, 175, detector 3, and 180 millimeters, detector 4, and this detector was directed to 90 degrees to the source's axis. The plasma source's unit was fixed to the rod on the manipulator, which allows to rotate the source about the vertical axis. This source was rotating. In this slide you can see the pictures, the photos of the plasma sources at different voltage of feeding secret. 4 kilovolts and up to 13.5 kilovolts. You can see that on each photo there are the plasma traces which spreading on the solid angle about 60, maybe 70 degrees, and when the voltage grows, the plasma torch is forming on the axis of the plasma source. And the experimental results. In this diagram one can see the results of measuring by Ui. Sorry. Pardon. Measuring by first detector. The detector is directed to the axis of plasma source. One can see that there is very wide spreading of plasma in this case, up to 80 degrees of solid angle. But there is also some portion of plasma that spreading up to 110 degrees. What does it mean? It means that plasma spreading down to the surface of plasma source is backward direction, on the backward direction. This slide shows the same measurement, but for smaller current. The smaller current, 8 kiloamps. This picture is in common the same. One can see the high wave in front of the plasma front, and spread and very wide spreading of plasma. This is another view, the alternative view of our experimental results. If on previous diagrams the value of ion current depicted as the color of diagram. This is the spectrum, which shows that ion currents was in range from 0 to 10 ampere on the centimeter square. And at this view, one can see that the alternative view, and you can see the wide spreading of plasma flow. And at this time, the value of current ion current is the distance from the 0 point to the each directions. The measurement of perpendicular detector was depicted on this slide. In this slide, one can see that the spreading of plasma, in this case, is more narrow, and almost all plasma was less spreading in the angles less than 40 degrees. This is two slides which shows the diagrams from 8 kiloamperes and 11 kiloamperes. This is the alternative view, which shows that in the case of the 4 detector, which is directed to the 90 degrees, the spreading of plasma is more directed to the source, or the direction axis of source. And if we detailedly review the waveforms of signals from the first, second and third and fourth detector, we can see the formation of solitary waves. At the initial moment, the sharp short peaks of the ion current are observed. After 5 microseconds, the signal becomes smoother. A detailed view of the sharp peaks at the beginning of the ion flow is shown in the figure. The front of the ion flux has an explicit structure, which is repeated for detectors, located opposite to the plasma source, first, second and third. There is a weak positive peak at the beginning of a signal, weak positive peak. This peak corresponds to a flow of ions with high velocities, which are formed during pulsed surface backdown on the dielectric. A peak positive signal is followed by the noticeable negative signal. This signal can correspond to a wave of hot electrons, the energy of which can exceed the bias across the Faraday cap, about -30, -80 volts. The hot electrons wave velocity for current 11 and 8 kiloamps. You can see that this velocities is about 10 or 20, 10 to 6 power centimeter per second, which is much greater than usual velocities in the vacuum arc, which usually estimated to be about 2 centimeters per microsecond. And the velocities of solitary waves. You can see that its velocities so to very big, about 5 or 15, 10 to power 6 centimeters per second. And we suppose that this solitary waves have the nature of shock acoustic wave, which velocity can be estimated as following to this formula, whereas the temperature of electrons is not the temperature of thermal electrons, but this temperature of so-called effective turbulent electron temperature, the temperature of electrons in the turbulent oscillation inside the plasma. According to this figure, the velocities of solitary waves calculated in the same way as of electrons do not change much with distance. Sometimes exception occurs, but this behavior can be explained by the process of nonlinear interaction or decay of the waves. And conclusions. It can be concluded that intense nonlinear waves are present at the beginning of the ion flow. This fact must be taken into account. These nonlinear waves can strongly influence in the ion flow parameters during further usage. These measurements show that at a distance of 150 millimeters, the ion flux becomes predictable and stable after 5 microseconds after the start of plasma generation. The high plasma density propagates at speed of about 0.5 10 to power 6 centimeters per second. Thank you for your attention.